Thank you. Excellent. I got to go to AAS this year at wherever it was, downtown, Convention Center.
Yes.
There was like 3,000 people there. And the thing I liked to do the most was go to the preface conferences. And I was really impressed with somebody that was coming to talk about M33, Triangulum. And he had some news to release there. And I was able to go up and we talked for a few minutes and I said, how would you like to come talk? So we figured out a date and here we are. So it's really great. And Professor Adam Smercina is a professor here at the University of Washington, live in Tri-Cities. And we're really glad to have him here to talk to us about companion galaxies and other galaxy stuff.
Yeah.
Is that good?
Yeah.
All right,
good.
take it away.
All right, cool.
All right.
I'm gonna unplug you here. All right. So let's see here.
Oh, and then Keith, could you stop sharing?
Oh, stop sharing.
That's actually, I might be able to. Oh no, wait, we're good.
You okay?
We're good.
I'm not sharing anymore.
Yeah.
Okay. And now is everybody seeing this on Zoom?
Yeah, everybody's seeing on the Zoom.
Good. All right.
And then, Adam, let us know when you want us to, if you want to shut down the lights.
Yeah, do you mind if I just do this? Yeah, why don't I just do that now?
Let's do it. All right. Let's get really
I'll
cool.
try to keep everybody engaged so nobody falls asleep.
Yeah. Ooh, nice. Ooh.
We need the darkness to see all the lovely stuff here. So yeah, thank you again to Keith for inviting me to come talk today. I'm really excited to be here and share some of the work that I've been doing on the Triangulum Galaxy. So I'm actually a postdoctoral researcher here in the department at UW, the Department of Astronomy, and I have. Let's see here. There we go. Not that there's going to be a lot of recognition of any of these names, but I just wanted to put this slide up to sort of hammer home that science is a very collaborative process, right? So there's been a ton of people that have worked on this project alongside with me that have made all of this stuff possible. And I want to start this talk off by orienting us to sort of our cosmic neighborhood, so to speak. So this is an artist's conception of the Milky Way. Obviously, we can't really see this. We're inside of the Milky Way. And the Milky Way has a couple of large, what we call satellite galaxies, dwarf galaxies that are gravitationally bound to it. And these are the Magellanic Clouds. And the Magellanic Clouds are actually visible with the naked eye in the southern hemisphere, too far north here, but they are visible. And the Milky Way has a neighboring galaxy, M31, also known as Andromeda, that is similar in mass and similar in structure to our Milky Way. And M31 has its own dwarf satellite galaxy, and this is the Triangulum, the star of our show today, also known as M33. And you can see right away that M33 is a much more sort of beautiful, put together spiral galaxy compared to, for example, the Large Magellanic Cloud, which is very similar in mass. And one of the reasons for this is that M33 is actually quite a bit further away from M31 than the Large Magellanic Cloud is from the Milky Way. And in addition to these larger dwarf galaxies that I've named here, there are a bunch of other smaller dwarf galaxies that orbit each of these larger galaxies as satellites. And as an ensemble, all of these galaxies form what we call the local group environment. And the distance between the Milky Way and Andromeda is something like 800 kiloparsecs, or 2.5 million light years. So I've already shown you a number of different galaxies that all look very different, right? And so this is kind of telling us already galaxies come in all shapes and sizes. And we've been building this intuition for about the past century. And so this is an example, a very modern version of something that was originally called the Hubble sequence, or the Hubble tuning fork diagram, named for Edwin Hubble, who did a lot of the early classification of the structure of galaxies in the early 20th century. And we're not going to talk about this part of the diagram much. These are elliptical or spheroidal galaxies. We're going to focus on the spiral galaxies in this diagram. And spiral galaxies come in kind of two flavors. Those along the bottom are galaxies that have what we call a central bar, which is exactly what it sounds like. There's a rectangular or kind of linear structure in the middle of the galaxy that that sort of attaches to the visible spiral arms. And this turns out to be a little more than half of spiral galaxies in the nearby universe have something like this, these central bar structures. And the other piece of the tuning fork here, they have no bar. And so these galaxies to the left part of the diagram here, these spirals, are what we call early type spiral galaxies. It's very confusing nomenclature, but that's what we call them. And these are typically more massive spiral galaxies. And you can see as you sort of move to the center of this diagram, you start to get what we call these grand design spirals, these very perfect kind of two-armed symmetric spiral galaxies. And as you move to the right, you get these more late type spiral galaxies that are less massive and also have these kind of many-armed structures. The pinwheel structures, you start to get something we call flocculent structure. I mean, there's kind of wisps, a bunch of little wisps of spiral structure around the galaxies. And so these late type spirals are typically lower mass. But then you have at the very rightmost edge, this actually becomes less of a tuning fork and more of a tennis racket or something because of the recent addition of these irregular galaxies that we've classified in more recent times. And these irregular galaxies are even less massive than the late type spirals. And you can see they don't really have any spiral structure or obvious disk structure at all. And it turns out that we don't really understand this transition very well for this sort of mass-dependent transition for when spiral structure starts to emerge in these low-mass disk galaxies. And one of the reasons for this is that the nearest examples of these galaxies that we have, the Milky Way's own Magellanic Clouds, are kind of a mess. So they actually sort of straddle this transition region, or should straddle this transition region between galaxies that are mostly irregular, which are galaxies that are similar in mass to the small Magellanic Cloud, versus low-mass galaxies that have spiral structure, which are similar in mass to the large Magellanic Cloud. But the problem is these two galaxies are interacting, and it's messed up their structure that they used to have quite a bit. And so it's kind of difficult to understand the evolution of these two galaxies when they are sort of gravitationally disturbed in this way. A much better example is M33, right? It's very similar in mass, it's very close to this kind of transition region where spiral structure starts to emerge, but it's a much more orderly galaxy. It's not really being obviously disrupted by anything, and it makes it a good case study for these purposes. So when I talk about galaxy structure, what am I actually talking about? What are we actually measuring? Because galaxies aren't, we know looking up at the sky, the Milky Way is obviously not some solid body, right? It's made of stars. You can mostly see the stars. Also, if you have a particularly dark viewing site, you can see that it's made of dust, and it's made of gas as well. You can't see the gas so much. But stars make up most of the visible light of galaxies. But gas and dust can also be illuminated at different wavelengths, particularly in regions where young stars are being born at high rates. So I want to show this example. It's also just an opportunity to show beautiful new data from the James Webb Space Telescope of a nearby galaxy. This is just some nearby galaxy in the Messier catalog, M74, from the FANGS survey. And on the left here, I'm showing the image seen with the Hubble Space Telescope. And this is at visible wavelengths. And on the far right, I'm showing the view as seen by James Webb in the infrared, and the central panel is combining those two images. So you can see that there is there are differences in the structure of this galaxy depending on what you're looking at. So the visible light is mostly dominated by the light from stars, but you can also see filaments of dust. You can see these red blobs of emission. This is from ionized hydrogen, something we call the H-alpha emission feature. And when you look in the infrared, you see that many of those regions that look like these dust filaments that are actually obscuring light in the visible regime are now radiating at infrared wavelengths. And you can even see some of these same features that are glowing in gas and dust, as you can see in H-alpha emission in the leftmost panel. And you can see when you look at the combined view, you can see things like this hole here where there is no dust, and you can clearly see the stars in between. But basically, the point of this slide is just to say that galaxies are really made up of a bunch of different things, right? Layers of things, and their structure, how we determine what structure a galaxy has, it depends on what wavelength of light we're looking at, which component of a galaxy we're looking at. And so if we apply this idea now to M33, this is M33 at different wavelengths of light. And so the wavelength of light is increasing as you go to the right of these plots. The leftmost panel is showing an image of M33 in the ultraviolet from the Galaxy satellite. And you can see that the emission is very kind of knotted, structured. This is because the ultraviolet light is dominated by very young, hot stars that are all clumped together. The optical or visible light image here in the center is a composite from the VLT, the Very Large Telescope. And you can see, again, those kind of clumps of star formation seen in ionized hydrogen, H-alpha emission. But you also see the light from stars, right? The rest of this light that's not these little red blobs. But when you look in the infrared, you again get kind of a structure that, this is from the Spitzer Space Telescope. It looks very similar to kind of knotted, very highly structured image that you see in the ultraviolet, but this is now the emission of dust and gas in M33. And there are some differences. Some of the regions that are very bright in the infrared are actually pretty faint in the ultraviolet because the dust is obscuring the light in the region. But as we look across these different views, M33 seems to have a pretty similar structure, right? You would say that it kind of keeps this pinwheeled, kind of many-armed, many-spiral-armed structure across these different views, even if in detail things look a little bit different. But what we really want to know is what are its stars doing? And the reason that we want to study the stars of M33 is because this tells us about the sort of evolutionary history of this galaxy. It's not something that you can really get at with these sort of traditional images, right? And so in order to study the individual stars and stellar populations in M33, we used the Hubble Space Telescope. And so here I'm showing this optical image, visible light image of M33 again, and with this central region showing now the cutout of this Hubble imaging survey. And you might say, this is a lot smaller than the nice, beautiful ground-based image that it's sitting on top of. Why use Hubble at all? And the reason we use Hubble is because it's a lot easier. In fact, it's impossible to do from the ground. It's basically impossible to resolve these individual stars in a galaxy this far away with a ground-based telescope. And this is due to the atmosphere. So when you're looking at the sky through the Earth's atmosphere, there's a sort of floor that's set. We call this the seeing that limits the spatial resolution that you can achieve for telling apart objects in an astronomical image. And this is something that many of you, if you're into astrophotography, you may be very familiar with the seeing conditions, right? Good seeing is something like an arc second. And very good or excellent seeing is more like 0.5 or 0.6 arc seconds. This is something you can only achieve several places on Earth. Right? Mauna Kea, the summit of Mauna Kea on Hawaii is one of these places. But even though the Hubble Space Telescope is this small little telescope, it's much smaller, for example, than the very large telescope that took this image from the ground. But it benefits from having diffraction-limited observing conditions. And this means that you're not looking through the atmosphere, and so it can now resolve things on scales that are proportional to 1 over the diameter of the telescope. And so, if the best you can do for seeing is 0.5 or 0.6 arc seconds, with Hubble, you can do 0.1 arc seconds or even a little bit better. And so, to show you the difference that this makes, this is a ground-based image of the globular cluster M92, which is a Milky Way globular cluster from the ground. And you can see that there are some stars that are resolved. But when you look at it with Hubble, you just see the difference. At least I hope you can see the difference. Many of these stars, in fact, that you see in the ground-based image aren't individual stars at all. They're just blends of a bunch of stars, tens of stars, that you can actually pick apart with Hubble. So Hubble is the ideal tool. James Webb, as well, is a phenomenal tool for this, space observatories in general. But the problem here, and I kind of alluded to it looking at this image over here, is that a galaxy as nearby as M33 is very big on the sky. So for example, the HST field of view, which I'm showing is this little orange square here, you can see is tiny compared to the size of this galaxy. And in fact, I just threw up the scale of the full moon for reference, which I actually found kind of amusing, that the half a degree size of the full moon is actually pretty comparable to the visual extent of M33. But you can see that we have our work cut out for us if we want to use Hubble to survey a large patch of this galaxy. And so you have to stitch together a lot of individual observations. You can kind of see the jagged edges of this field where we indeed have put together a mosaic of many Hubble observations. But it's worth it because you get data that look like this, and this is just a teaser where we can actually resolve these stellar populations and use it to study the evolutionary history of this galaxy. So this is the mosaic kind of blown up. This is an optical image combining the G-band light from the G-band and I-band filters on Hubble. And this is 108 orbits worth of the Hubble Space Telescope. It literally went around the Earth 108 times to collect the data that went into this project. So this is 54 kind of individual pointings of Hubble. And this image was created by UW grad student Meredith Durbin. They did a wonderful job putting this image together. And you can see lots of awesome details here. I don't know if my cursor's not showing up. Interesting. Oh, do you? Okay. Well, anyway, you can see the spiral arms really well. You can see that lots of blue young stars along the spiral arms, many of the different spiral features here. You can even see up in the top left corner of the image, NGC 604 is this very massive star-forming nebula that actually made its way into the NGC catalog as a separate object. It's part of M33, but it's bright enough that it made its way into the catalog as a separate thing. But now I'm going to take this beautiful image and blow it up and show you. Oh, great. Pointer, great. Excellent, thank you. Yep. Good. Okay. Oh, and my cursor's back. Whatever. All right, we're going to zoom in, so it's fine. And now this is showing you the power of Hubble, right? So now this image has turned into this sort of million grains of sand here. And each of these grains of sand is an individually resolved star in M33. And you can just see the incredible detail here. So you can see things like little open clusters of hot young stars up here, this cluster of blue objects. You can see the dust in just incredible detail. The dust is reddening all the stars that live behind it, causing them to appear redder than they otherwise would. You can see older individual star clusters here. It's just an incredible data set. And so all told, across this entire footprint, we've resolved 22 million individual stars in M33. But now I want to go a little bit into some minutia here and tell you what we can actually learn from these 22 million stars. And specifically, the properties of these stars that we measure can tell us when they form. So this is a diagram called the Hertzsprung-Russell diagram. And this is an artist's conception. Along the x-axis here is the surface temperature of a star. And so hotter temperatures are to the left here, and they're bluer. Cooler temperatures are redder to the right. And I'm going to explain why that's sort of flipped relative to your intuition. And then this is the luminosity, or the total amount of energy emitted by the star on the y-axis here. And you see some features here. So this is the main sequence of star formation. So when stars are born and begin forming hydrogen in their cores, they fall on the main sequence. And you can see the sun lives about halfway down here. And there's some other features that lie off of the main sequence. And these are where stars of different masses evolve to once they've spent all of the hydrogen in their cores, and they move on to this kind of post-main sequence evolutionary phase. So to point out a couple here, supergiants is a stage of evolution that very massive stars evolve onto. We also have these red giant stars, which many of you have heard. And this is something the sun will eventually become in 5 billion years or so. And if I just draw kind of a little track, the evolutionary track of the sun, it's going to look something like this, and it kind of overlaps with the supergiants. That's just it doesn't become a supergiant, but it will eventually become a red giant star, become a planetary nebula, and then eventually evolve down into a white dwarf at the end of its evolution. But this is really a theoretical view of the evolution of a star. It gives us a very detailed kind of theoretical framework for how to interpret the observations of stars that we have. But temperature, the surface temperature of a star, I mean, I can't go out and stick a thermometer into the atmosphere of a star and tell you what temperature it is. I don't know a priori the luminosity of a star because I don't know exactly what distance that star is away from us, right? And so we need to turn this into something that's more observationally focused. And so up here I'm showing 4 different spectra of different types of stars. And so this spectra, these are the wavelengths of light versus the brightness. And so this is the UV going all the way to the mid-infrared. And this is to the leftmost spectrum here is a B star. This is a very young, massive star that's on the main sequence. And then over here you have an M star, which is a very low mass, cool star that is also on the main sequence. The spectra of these different stars are very different, such that if you took a telescope filter, for example, say we took the U-band filter and the V-band filter, and you imagine the amount of light in the U-band for this B star is going to be more than the amount of light that's in the V-band for that star. And you're going to swap that for the M star. Right? It's going to be brighter in V-band than it is in U-band. And in this way, kind of comparing the brightnesses of stars in these different filters gives us an estimate of their color, right? Are they brighter in the bluer wavelengths, or are they brighter in the sort of redder wavelengths? And that's where that the temperature color dependence comes from. And so we can then take these colors of stars that we measure in these filters, and their brightnesses and combine them into something called a color magnitude diagram. This is an observed kind of observational version of this Hertzsprung-Russell HR diagram. And so again, hot stars live on the left here, cool stars are on the right, and stars that are fainter are on the bottom, brighter are on the top. And I'm going to show you how this color magnitude diagram is populated with stars depending on when they form. So as a starting point, I have this little sliver of stars that formed 10 billion years ago. And this is about where stars that formed 10 billion years ago live in this color magnitude diagram. And so now we're going to watch it evolve, right? As you have younger and younger episodes of star formation, or more recent, I should say, you can see that this color magnitude diagram becomes populated with stars in a way that we can select kind of broad regions where we kind of roughly know the ages of stars. I'll just let that go again. So you can see most of the old stars kind of live over here. You're starting to get younger stars in here, and very young stars this is actually the main sequence that starts to appear over here. Okay, so now taking this idea of a color magnitude diagram, this is what the 22 million stars that we've resolved in M33 end up looking like. And so this is the exact same as the previous slide. This panel over here is the color magnitude diagram in a couple of optical filters. And this is the color magnitude diagram in infrared filters. And so I've labeled a couple of regions here. So for example, this purple region, pink region over here, this is where very massive and young stars live in M33. We're not able to resolve the main sequence down to kind of lower mass stars like the sun, but we can see very bright stars and very massive stars that are on the main sequence. And so these are very young, right? These are several million years old, less than 10 million years old or so. And then this region, these are still very young stars, slightly older. These are actually stars that have evolved off of the main sequence, but they're still very, very massive hot stars. And then when we look at the infrared color magnitude diagram, which is just a little bit easier to select kind of the older stars, you can see this region here is where the very oldest stars live. This is the red giants, right? The red giant branch stars live kind of in this region of the diagram. And then you also have these very old stars. These are asymptotic giant branch stars, but they're also very old. So now we can take these sort of four very broad regions where stars of different ages should live, and we can look at how they're distributed on the sky in M33. So each of these plots is showing the density of stars in this different age bin, color mapped to according to this color bar on the right of each of these panels, where lighter colors, yellow, white, those are higher densities of stars. Darker colors are lower densities of stars. And we see some very interesting things here. Mainly, when we look at the very oldest stars, we see a structure for M33 that's completely different than we would expect when just looking at an image of this galaxy. It's mostly a kind of smooth disk structure with also two kind of dominant or primary spiral arms and a central bar structure. And I think I mentioned that the typical structure of M33 in a normal astronomical image is this kind of pinwheel spiral with no visible central bar. And so this is very different. And this kind of typical structure that we're used to thinking about for M33 is really only apparent when we look at the very youngest stars, these two bottom panels here, where you start to get this kind of pinwheel structure that we're used to seeing. And so to convince you quickly here that we're not just, we do a little bit better than just kind of squinting at the pictures and saying, I think it looks like it has, two arms versus whatever. I'm going to get a little bit quantitative here. So if you imagine a star that's living in M33 here, and it turns out that really for most galaxies, you can approximate the shape of a galaxy using an ellipse. And so if this is the ellipse that I use to approximate the kind of light distribution for M33, then I can describe the position of this star using an elliptical angle and an elliptical radius corresponding to the semi-major axis of this ellipse. And so then if you consider a bunch of concentric ellipses, right, you could then assign an elliptical angle and an elliptical radius to every single star that we observe in the galaxy. And then if we plot those coordinates on a diagram, this is the natural logarithm of the elliptical radius, but still it's a radius versus elliptical angle plot, then we should see some specific features we should see some specific features in this plot for specific features in the galaxy. So for example, a bar, which is this kind of rectangular linear structure, this bar should really have a fixed elliptical angle. You can see that it kind of occurs at the same angle along all of these ellipses, regardless of the radius of the ellipse in question. And so you should see two of these, right? So if you split this down the middle, you imagine going around one way, you see it on the one side, and then you go around the other side and you see it again. So you should have two horizontal lines corresponding to this kind of bar feature. The spiral arms are also pretty well described in this diagram. So they can be described by a logarithmic function in radius. So the shape of these spiral arms are typically described by a logarithmic function. And so as you go out along the wrap of the spiral, you should see something that looks like this, which is kind of a linear feature in this diagram as well, but it has some slope to it, and that slope tells you about how the spiral arms are oriented. Okay, so now that I've set this up, hopefully, we see the exact same thing. Okay, this is why I've chosen to show that. So this is, again, each of these four panels is the different bins of stellar age that I kind of described, right? And we see exactly what I set up in the previous slide. We see these two parallel horizontal features that indicate this bar structure. And we can use this to measure, for example, the extent of the bar, which is about 3,000 light years across in total. And we also see these kind of two primary spiral features, at least in the older stellar population. But when we look down here, when we go to the young stars, for example, you see similar structures as you see to these top two panels. But when you get to the very youngest stars, things start to get really messy, as we kind of saw in the density maps of these stars, where if you know where to look, you can kind of see these structures appearing, but it's a lot messier. You see a lot of these other little structures appearing, and this is where this kind of flocculent or many-armed structure is starting to happen. But it's very different, right? We see quantitatively a very different structure when we look at the oldest stars in M33 versus the youngest stars. And so the question is, why are these two different populations of stars so different? So here again are the density maps for the very youngest stars and these old stars, as I've labeled them. And I just want to show kind of the approximate locations of the spiral features that you can see visually in each of these maps. There's definitely these two dominant ones over here. Over here, maybe there's 5, maybe there's 6. It's kind of hard to say. There's a lot more than in the other image. And so what I want to use for comparison and how we interpret this, I'm going to go back to this image from the Spitzer Space Telescope of the gas and dust in M33. And specifically, this region here corresponds to approximately what we're looking at for each of these two panels. And you can see, hopefully, that the structure of the gas and dust is much more similar to the structure of the young stars than it is to the structure of the old stars. And so this is it. This is the answer, right? The young stars look different from the old stars because they're born out of this gas. And the gas looks very different from the distribution of the old stars. Now, why the gas is so differently distributed than these old stars. Sorry, something I forgot to mention. These old stars are important because they're 95% of the mass of stars in the entire galaxy, right? So that most of the mass of M33 lives here, right? This is a few percent. And so it's really kind of curious that the gas is doing something so different from the stars. In the Milky Way, for example, you see much more coherent structure between the gas and dust and the bulk of the stars that live in our galaxy. And so this is something that we're interested in studying more. We think it has something to do with the disk of M33 being so low mass, and the physics of the gas is just it behaves somewhat differently than it does in larger spiral galaxies. But we do think that it's something that may be important to understand lots of different nearby spiral galaxies. It turns out that we have a lot of these so-called Magellanic spirals in the nearby universe, meaning they're all very similar in mass to the Large Magellanic Cloud. And so I'm showing a few of them here. NGC 2403 is, I believe, about 6 million light years away, and it looks almost identical. Like they could be twin galaxies. And NGC 300 and NGC 2976 are a little bit further, even more further out. But yeah, I think this intuition that we built studying M33 may be useful in helping us to understand kind of the formation, the evolution of this whole family of kind of low mass spiral galaxies. So the last thing I want to talk about and share is that we discovered something else interesting in this analysis of specifically the older stellar populations in M33 that, like I said, trace the bulk of the mass. And so what's interesting is that these two dominant spiral arms that we see in M33 are not symmetric, right? So in kind of traditional spiral density wave theory, the two spiral arms that a galaxy has should be the same strength, the same sort of enhancement above the density of the rest of the disk, and they should be 180 degrees apart, right? Those are kind of symmetric spiral arms. And so M33's arms are asymmetric, not only in terms of their angle with respect to each other, about 20 degrees off of this kind of 180 degree symmetry, but the southern arm is actually about twice as strong as the northern arm. And these kind of asymmetries are really a strong indicator that a galaxy has undergone some kind of recent gravitational interaction. And this jives really well with what we understand about the outer structure of M33. So this is again the optical image of the galaxy. If this is representative of the sort of extent of the disk, now I want to show you the distribution of neutral hydrogen gas. And within the disk, things look pretty good. These colors tell you about the velocity of the gas. So redder colors, the gas is moving away from us. Bluer colors, the gas is moving towards us. And so this inner disk shows the kind of ordered rotation that you would expect for gas in a spiral galaxy. But as you go to the outskirts, you can see that the gas is twisted. And it's not just twisted in its sort of visual distribution, but it's twisted in velocity space as well. And this is a smoking gun for a gravitational interaction with another galaxy. And so together with the kind of signatures, asymmetries that we're seeing in the inner disk, and these kind of outer radii twisting of the gas that we see. Sorry, we also see twists in the stars. This is the distribution of stars in the red. And so all this together tells us that M33 interacted with something quite recently. So then the question is, who did M33 interact with? So it is, going back to the very beginning of the talk, it is a satellite of M31, Andromeda, which lives right here. And on this figure, M33 is down in the left corner. This is now a plot showing the density of stars that have been detected through large-scale surveys in the very outskirts of the Andromeda Galaxy, forming what we call the stellar halo of Andromeda. And what's really interesting is that this sort of twist in the distribution of stars that we see in M33 really has this telltale signature that it's pointing straight at M31. And so we would naively say, of course, these galaxies must have interacted. It's pointing right at it. We know it's gravitationally bound to this larger galaxy. But it turns out that the evidence is kind of muddy. There's some evidence from the motion of these two galaxies. People have done some work modeling a possible past interaction and haven't found a lot of support for these two galaxies being close together at any point during the last few billion years. And so it's this kind of puzzling, thing. We're not really sure. But one secondary possibility is that we now think that M31, a few billion years ago, interacted with another galaxy that was even bigger than M33. And it caused the creation of this kind of stream feature that I'm circling here. And so something that we've considered is that it's possible that if M33 didn't interact with M31, maybe it interacted with this previous member of the Andromeda group that has now been sort of cannibalized or disrupted through an interaction with Andromeda. But this is something that we're really interested in understanding better in the future here. Okay, so to summarize, we've conducted this Hubble imaging survey of M33, where we've resolved 22 million individual stars. I just love saying that, 22 million. And we've used these stars to reveal some pretty interesting things about M33, mainly that the old stars, when we look at the oldest stars, they don't show this characteristic pinwheel or flocculent structure that we're used to seeing for M33. They show this kind of two-armed barred structure instead, and it's really only the youngest stars which follow this kind of pinwheel structure that is also seen in the gas and dust of M33. And finally, we confirm that our observations of the inner parts of M33 also show this consistent story that M33 interacted with something in the very recent past. And we're not sure if this was Andromeda or a possible former group member that has since been disrupted. But this is, I think, the focus of one of the main focuses of my contribution, at least, to this program, is to try to understand better the evolutionary history of M33 and its status as a sort of satellite of Andromeda. All right, that is all I've got. Thank you.
Lights?
Yeah.
All right, brace yourselves, everybody. All right, not too bad. Thank you so much. And we'll, let's go over some questions. Maybe go back and forth a little bit here. Yeah. Keith, why don't you?
Just a quick one. I should know the answer to this. I think I have known it, but is M33 turned toward us? It's not flat on, is it? Or is it turned?
Oh, yeah.
Does
so
that matter when you look at the shape of arm?
Absolutely. So that's a good question. I actually don't know the answer. I'll hedge a little bit, deflect a little bit by saying that's actually a really hard thing to measure. So knowing, you can tell that a galaxy is tilted some way But it's funny how when we look at galaxies, I don't know about you, but I often have a guess. I'll think, my brain wants to interpret that it's tilted one way versus the other. But it's actually almost impossible sometimes to tell which way that it's tilted. I think that the eastern half, or no, the western half is tilted towards us. But I'm not sure. Yeah.
But it would make a difference in how you perceive the arm.
That's right. We use something called deprojected radii for doing these things, right? So there's a trigonometric term that you can use to get rid of that effect. But yeah.
We got we'll go back and forth a little bit. We got a question online.
Okay.
Chen asks, what features of the galaxy do you use to differentiate the ages of the stars from the Hubble image? So what features of the galaxy do you use to differentiate the ages of the stars from the Hubble image?
Yeah, so this color magnitude diagram, so I'll bring this up again.
Thanks for the question, Chen.
Yeah, thank
Also,
you.
Gary Ferguson says, excellent and fascinating talk.
Thanks a lot. Yeah, so it's this diagram. I guess we can't see it very well, but we can see well enough. So it's these colors that we measure in different filters and the brightnesses of stars, and then pairing this with this understanding that we have from the stellar evolution models, that we're able to sort of draw these kind of boxes or rough regions where we know kind of the ages of stars. I didn't get into this, but I mean, you can do much more complicated things. So you can actually, you can fit this entire distribution of stars, and you can put in all of the sources of uncertainty that you have from your telescope and from your observations into a software model that you can then use to fit the entire distribution and get sort of more detailed ages than what I've shown here. But yeah, this is a way to do it.
Call out the in-person.
Sure. Right here.
Yeah, absolutely. Oh, yes. Do we ever put dark matter or factor dark matter into our thinking about these things? The answer is absolutely. So I want to show this slide again. So it turns out that dark matter is a huge part of this, right? Because we think that the reason that these group structures exist is because they actually live in huge halos of dark matter, right? And that's a super important insight for thinking about this, especially when we think about galaxies interacting. We have to think about the fact that they live in much larger halos of dark matter. Yeah, there's a lot of observational evidence for the existence of dark matter in things, but it's a fascinating thing. We have all this indirect evidence, and yet we don't know what it is. So yeah.
Thanks for the question, Russ. That was a good one. I have a question from Dave Ingram on Zoom. Dave, do you want to unmute yourself and ask?
Yeah, it's related to the age issue too. You call one set of data very ancient, and I assume that that's at an infancy, and then the others you call them very young. And is that more recent times or what?
Yes. Yes, that's a good question. So what I'm calling ancient and old, I guess, are typically the cutoff there is about 1 billion years. So stars that formed 1 billion years ago or more are what I call old or ancient. And then stars that are very young are stars that are maybe less than 10 million years old or something like that.
Just recently birthed.
Exactly, right. And it's important. It's an important distinction that because of how far away M33 is, when you have a population of stars that are born, stars of all masses are born, right? But we're only in M33. We're only seeing these young stars are only the most massive young stars, right? That's all we're able to see.
Thanks, Dave. Um,
So what's the age range from ancient or infancy to the current age? What age range are we looking at?
Yeah, so we can see well, we can see stars that are a few million years old, all the way up to billions of years old.
I, yeah.
Do you have to, I'm guessing the answer is yes. Do you have to subtract effects of the absorption by dust from the chart diagrams?
Yes.
How do you tell the difference between a blue star behind the dust and a red star?
It's a great question. So actually, yeah, sorry. The question was about the effects of dust when we're looking at these HR diagrams, these color magnitude diagrams, and how we tell what the effects of that dust are. So there's actually a few different effects that we have to deal with as far as dust goes. So there's dust in the galaxy, and this is what I was showing, in the image. You can see the dust that's in M33. It's affecting the stars differently. There's also dust in the Milky Way, and so it's along the line of sight. So the dust in the Milky Way, we actually have very detailed maps of what the dust looks like in the Milky Way, and there have been models that people have done that you can just apply to different filters and subtract those effects of the Milky Way dust. The dust in M33 is much more complicated. I haven't done anything with the dust in M33 in these diagrams. And so what that means is that, oh, you can't see it very well. But so this feature here, there's a feature here where stars sort of pile up, right? There's an evolutionary point. It's called the red clump. And stars pile up here. And because there's so many stars, you can actually see the effects of dust extinction. And so this thing that should be a little ball in this diagram becomes this spread out thing. And that's exactly because of dust, right? So there are stars down here that are way redder than they should be and fainter than they should be because they're extinguished by dust in M33. Now the infrared diagram is a lot less affected by this because dust does not obscure infrared light as much as it does optical light. But it's something that we have to take into account. It's actually something I'm working on right now, is to try to sort of map the levels of extinction by dust across the face of the Hubble survey. Yeah, that's one way to do it. Sort of the spread in features where we sort of know how wide they should be theoretically, and then comparing that to how wide we observe them to be. That's another way that you can get a handle on it. But yeah, definitely this is one of the novelties of this survey is that we have 6 different filters, and so having the UV all the way through the infrared helps us do things like account for the dust for sure. Yeah.
And I have one more online question. This one's about just black holes in general. It seems like so, not specifically M33, Alan asked, but if there are more ancient old stars in the galaxy, are there more black holes? And how are those determined?
Oh, that's a good question. I don't know. Yes, probably. Yes. Yeah. So that's an interesting question, actually. So black holes are an outcome of stellar evolution. And so if you have a galaxy that, for example, has just formed more stars over its lifetime, well, it's not just about how many stars you form, right? So in order to form more massive stars, you have to have more intense star formation. That's sort of how it works, right? So in areas where you have more intense star formation, higher rates of star formation, you end up producing more higher mass stars that then will evolve into black holes. So that's an interesting question. I actually think this is something that we're going to get a handle on with some of the gravitational wave facilities that are starting to come online. I mean, LIGO is in the eastern side of Washington here, has done some of this work. But being able to sort of use the rate of the mergers between black holes to say something about how many black holes are in a specific galaxy, I mean, that could be an interesting thing to look at. But yeah, it's got to do something with it. I don't know. I don't study black holes, but
Thanks for the question, Alan.
yeah, thank you.
Keith, and we'll finish up.
Yeah.
We'll finish up with these three. Yeah.
Within the local group, you guys try to do another analysis of another local group, galaxy, or pairs and stuff.
Yeah, absolutely. Actually, this is the contrasting galaxy. The original survey that used this this technique, I'm showing here. I had this. Where's the crazy acronym? There. Yes, the panchromatic Hubble Andromeda Treasury Triangulum Extended Region. So the FAT, the original, was targeting M31 Andromeda, and it used a very similar technique. I don't think I have a slide showing it, but M31 is even bigger on the sky, and so FAT was an even larger survey, and it was only able to do like 1/3 of the disk of Andromeda, but they worked out a lot of the kinks and kind of refined this technique with that. Yes. So one of the things for M31, we're actually publishing a paper on this very soon. So the difference in the structure of the old stars versus the young stars, that's something we don't see as much in M31. And this kind of goes back to this idea that I mentioned that bigger galaxies, more massive galaxies, seem to have closer coherence in the structure of the gas and the bulk of the stars. And so that's something we do see in M31. So that's a difference with this particular galaxy that we didn't see with FAT. But yeah, I mean, overall, it was interesting to see what the stellar populations looked like in this smaller galaxy compared to this much larger galaxy, because M33 is about 10 times less massive than Andromeda, and yet its star formation rate is actually higher. So there's a lot more young, massive stars in M33 compared to Andromeda, which is a bigger galaxy. So, yeah.
Is M33 something you had your eye on, or is it out of necessity that you're studying it? And what is something that you do have your eye on? What is time on the future?
Oh, that's a good question. I think, this is a very large collaboration, and I think overall, I mean, it was accessible, right? It's a very close by galaxy, and it's a very well studied galaxy, and so I think it was a pretty obvious target, and especially with the kind of success of the original FAT program studying Andromeda, I think there was a sense that it would be very interesting to compare what we found in Andromeda against its large satellite galaxy. And this is something that we've been kind of comparing and contrasting the Milky Way and the Large Magellanic Cloud, for example, for a long time. So this was kind of doing this in a more distant galaxy pair. I'm really excited about the capability of James Webb and some of the science that we're able to do with it. I think many of you might be familiar with the Cigar galaxy, Messier 82. M82 is a really interesting target that I'm excited to use James Webb to study in the future. It has it's edge on, and it has a lot of dust. So doing this kind of thing with Hubble in the visible range is impossible, right? You can't resolve the stars because there's too much dust in the way. James Webb is actually even higher resolution than Hubble, and it also sees in the infrared, and so this really helps us a lot. So Messier 82 I think is a cool target that I'll be excited about in the coming years. Yeah. Oh, that's a good question. So this is a NASA-funded program. So the way that observations with the Hubble Space Telescope work is that you propose through a sort of standardized proposal process to take the observations. And those observations, if your proposal is successful, They come with funding. You have to sort of justify how much funding you're asking for. But it's all funded through NASA since Hubble is run as a NASA facility. Yeah. No, it's typically one proposal. We all kind of are on one single observing proposal, and then the funding is divided up among the institutions that the members of the team belong to. So we have a UW funded group working on this galaxy. No, we get a few years at a time, and then you sort of, you have to justify if you need an extension on the project or something. But it's typically, these are typically 3 to 5 year funded projects, depending on how big they are. This was a very well-funded project because it was so much observing time with Hubble. Yeah, it was a big grant. Yeah, exactly. Yeah, that's right.
And go ahead.
So these 22 billion stars that you found,
Yeah.
are they named?
How
does this thing work?
That is.
There are so many galaxies.
Yeah.
Stars.
Yeah.
How do you keep track of anything?
It's a great question. No, they're not named. Not even every star in the Milky Way is named now, What I always find fascinating, even as a professional astronomer, I always find it fascinating, I find a dark sky site. I live over in Eastern Washington, and so the skies are pretty dark out there. And, you look up and you see the band of the Milky Way and whatever. All of the stars are within a 10 parsec bubble from Earth, right? 30 light years or something like that is all the farther you can see. And then there's all the rest of these billions of stars in the Milky Way. And so, yeah, it's interesting even sometimes to contrast that, right? There's countless stars up in the sky, and it's just a tiny little sliver. So, yeah.
So the resolution of the star,
Yeah.
what good does it do? What is the use of resolving the stars and having them identified one by one?
Oh, well, to tell you the ages, right? To tell you the ages and other properties that we can learn about the stars. Yeah. Exactly. Yeah. We think about these things as a population of objects, not as maybe individual objects. But I will say that there are really cool active areas of research for individual stars in the Milky Way, and potentially someday for galaxies further out in the local group. Things like the abundances of heavy elements. There are, believe it or not, stars that are tens of thousands of light years away from us that have individual identifiers because, for example, they have some ungodly low abundance of heavy elements, and this is the lowest metallicity star in the known universe or something. So there are things that individual stars can be sort of known for.
And and I'll just last question to close before we close. Combining what is asked online, they're talking about how the Grace Roman space telescope comes online, and
Yes.
But I'm going to twist that a little bit. Does the Grace Roman, or what excites you the most to help you in your field that you're studying? Is it one of the telescopes coming out, Grace Roman?
Yeah.
Webb, or,
Yeah, I think the new facilities are going to be a huge help. So I'll just use the Nancy Grace Roman Space Observatory. What you can do with the Roman is this entire survey. Oh, this might have died. This entire survey here could be done in one shot. Right? You could do it in one shot because Roman has the resolution of Hubble, but 100 times the area, right? So you just imagine doing this entire thing in a couple of orbits or a couple of hours of observation time instead of hundreds. So that's going to be huge. Yeah.
Awesome. Let's give it up one more time.
Thanks a lot.
Thank you so much. Thank you so much, everybody, for coming out today. We're gonna hang out for a little bit. If you want to come say hi. But we got some more. Fingers crossed. Clear skies, everybody. Wishing everybody clear skies because it's starting to get to that observing season. And it's getting a little bit warmer one of these days. And then a lot of good stuff coming. So we hope you can be there in person coming up for all the fun events. So be on the lookout. Yeah, thanks again, Adam. Really
Yeah,
appreciate
thanks
it.
a lot.
Yeah. All right. See everybody online.
You're eating too much.